it's actually pretty interesting. So just to catch everybody up, this is DEF CON CTF. I'm Zardes. That's Adam D, the Adam Damon.
Hello.
Live from our respective locations, which is unfortunately not Vegas this year. DEF CON CTF happens in Las Vegas every year.
Since when?
Since like the early dawn of history. I've been going to DEF CON since DEF CON 9, so that's almost 20 years, and CTF has been there in a recognizable form the whole time I was going. The earliest kind of proto CTF that I'm aware of at DEF CON, which is where the earliest CTFs were, was something around 1996 or so. But it's one of these kind of gradual evolutions, and it's very hard to say, like the evolution of a chicken or something. It's very hard to say. That's where the chicken begins. So that's kind of a brief history of the world in a nutshell. This is DEF CON CTF today, now in 2020 on Saturday, August 8th. DEF CON in 2020 is a little different. We're all on online because of COVID, which is, comfortable, but also a little uncomfortable because we're used to every year seeing everyone's faces, all the teams struggling.
I think it's mostly this look, though.
Yeah, exactly.
Staring intently into a computer. It's one of those things, if people are quiet, things are going well.
Exactly. So we are hosting it online this year, which has some challenges. One of these challenges is that we had to mess with the schedule a bit. DEF CON CTF invites the top hacking teams around the world as selected through a series of pre-qualifying events, culminating in the DEF CON CTF qualifier. So it's Olympic style. There are a number of events where the winner gets invited to DEF CON, and there is one event where the top N teams fill out the rest of the slots. In this year, every year is a little different. This year we invited 16 teams to join us in total, several of which won pre-qualifying events, several of which won both the pre-qualifying events and anyways placed high enough in our qualifier event to be invited, and several of which got in through the qualifier event. These teams are from all around the world, and this was tricky for us because DEF CON is held online this year, not physically in Las Vegas. So running it on Las Vegas hours, as we usually do, wasn't very fair to teams based on their locations. There would be teams that had to exclusively hack in the middle of the night, teams that had to hack in the early morning, then teams that got to hack during the afternoon when we were, mostly all awake anyways. So we tried to make this a bit more fair by spreading DEF CON out. I'm going to share spreading DEF CON CTF out. Oh, Adam, you're sharing the schedule?
Sorry, I've been sharing the scoreboard from last year, what you were talking about. So,
oh, perfect.
So here we have the scoreboard from DEF CON Quals. You can see over 48-hour competition. The top team, AOE, just crushed and scored, I think, 4 more challenges more than the second place team, which was really impressive. And then, so like Jan was saying, so the top 16 teams qualified. You can see where they pre-qualified. So even though AOE dominated the pre-qual event, they our qualification event, they also won Plaid CTF. So that's how they qualified. Psycore pre-qualified through Code Blue. And so you can see kind of all the team names here. So now you want the schedule. I can put up the schedule and you can talk about that.
Yeah, absolutely. So to make things as fair as we could, we created an 8 hours on, 9 hours off schedule to maximize, just evenly spread the pain on everybody. We started the game much earlier. We started at 4 a.m. on Friday.
Much earlier.
Yeah, this is 6 hours earlier than it usually starts. The setup at 4 a.m., start at 5 a.m. so that we could then have these enough time to fully spread out the pain. So the game this year, the CTF is split into 4 shifts. Shift 1 is Friday at 4 a.m. Shift 2 was Friday at 9 p.m. Ending, each shift is 8 hours long, so ending at setup 9, start at 10, ends at 6. And shift 3 starts soon, 2 p.m. start, and then 3 p.m. start to 1 p.m. end, and then shift 4 runs right up until almost the closing ceremonies, and that's where, you know, finally the winner of DEF CON CTF 28 will be decided.
Woo!
So this is the recap for halfway through the game. Right now we're at the halfway point. Let me show you from a scores perspective what has happened thus far. I'm going to share a screen. All right, you see that? Perfect.
Yes, I can. What a beautiful diagram.
Beautiful diagram. All right, so this is the game, and then let's actually back up and see the game at the beginning.
Can we go in reverse? What if we want to watch it in reverse order?
No. All right. So this is starting from the beginning, Friday morning, early morning. For the first 13 ticks, every tick is 5 minutes. Nothing really happened. And then there's a challenge called Casino, where teams were hacking each other through blackjack on an esoteric architecture, and they really pushed far ahead. So AOE is the team that won qualifiers. They also pushed forward with the Casino and really built a dominating lead that was eventually closed by Team PPP, multi-time winner of DEF CON, by through the exploitation of another challenge. They kind of kept passing off leadership for a little while until AOE lost the lead pretty clearly because PPP shot ahead on a challenge that Adam will talk about, which was an exotic architecture that they had to reverse and hack. They built up this lead and basically stayed ahead for most of the second shift, which was started Friday night and ended early this morning. Adam, do you remember the last tick? 163? Awesome. So AOE has been starting to catch up at the end of that last shift. And the trajectory definitely seems... Oops. Talk to a speech is hard, or push to talk is hard.
My Discord broke, or your Discord broke, or...
Yeah. So AOE is starting to catch back up. So the top of the scoreboard is under contention again. If you saw in the middle of the scoreboard, teams were kind of going up and down as they developed attacks and blocked other attacks from other teams. We'll talk about the services a little more in depth that they did this on. And hopefully we'll be able to, by the end of the recap, actually launch them on our archive of old services so that you can see them as well. I'll show you the archive of old services, and then let's jump into the recap. Let's do this. Oops.
You missed an O. How long have you been doing this? 3 O's. This has messed up our deployments actually many times, where somebody accidentally in the challenge is typing it out and puts in 2 O's instead of 3, and nothing works.
So we created a website where we put in not all, but all of our prior challenges that can reasonably be run in an archived way. There's a lot of them here, from qualifiers going back to 2017 up until the very latest challenges that we're retiring because they've been played out in DEF CON CTF this year. You can hop onto Archive.oo, you can click on a challenge, log in, and we will spin you up a virtual machine that you can attack. And by the end of this call, hopefully we will have this ready for this year's challenges. Cool. Let's see. What else? I guess let's roll in with the challenge updates. Adam, you want to talk about Parallel first?
Sure. Yeah, I can do that. Let me share my screen and I will show you what the team saw. So this is kind of the team interface of there's a screenshot of the team interface. So when the teams log in, this is not something that you guys could actually see. This is something that, or the general public, this is something for the teams to play the game. And here, this was kind of information about the service. It really doesn't tell you much, just some kind of flavor text about the challenge. Can you figure it out and find the flag? Patches are limited to 100 bytes and patches to OS are unlimited, which means nothing to you until you download it. You download the patch and you'll see there's a file called parallel-af.tar.gz. That's the file that you can patch, and that the flag location is in service flag. So that's the flag you're supposed to steal, and you can patch as much as you want. So when the teams downloaded this challenge, they got a tar.gz, and inside of it there was an x86 binary called Manchester and a file called OS. And so essentially throughout the course of this challenge, what the teams had to realize, what this challenge was actually all about, was an implementation of this Manchester data flow machine from the late 70s, early 80s. And so kind of like I think Jan mentioned in the last, when we did the last public event here, the idea here is we want to see how teams compete and think about different, completely new and different types of machines. So normally, and the key difference, so for those that are familiar with a normal CPU, right, the CPUs that we have now, there's various registers on the CPU. They can hold data. The CPU can move data in from memory into a register, do compute on the CPU, and then move back into memory. And the way it does that is it also needs to know what instructions to execute. So there's also a pointer to some place in memory that's executions, and that it starts executing things. A data flow machine says, hey, we should do this in a completely different way. What if we made a machine that didn't have an instruction counter? So that's kind of the idea. And the idea is now, rather than, and let me see, there's this really good survey that I used a lot of this on, was this data flow machine architecture by Arthur Veen in, what was this, 1987. And so I can show you a really good example here of, yeah, so here you have a kind of a traditional normal machine where you have A is equal to X plus Y, B is equal to A times A, C is equal to 4 minus A. And so this is kind of a description of the control flow and the data flow of this machine. So you have your, so you have memory that's stored, right? This is traditional CPUs that we're used to, data that's stored somewhere. The data moves into the CPU and gets added together, and then data flows back and gets pushed back into. So we can see this first instruction. So the way this is source, destination. So plus X. So get X from memory, add those together and put the result in A. And then that dashed line is the control flow. And says the next instruction that's to execute is the next one, and so on and so forth. So this is kind of how normal programs work, how normal assembly works. And so data flow machines say, hey, we should do this completely differently. What about, instead of thinking of it in terms of where the control flow goes, what if we thought about the machine in terms of where data flows? So for instance, here we have a data flow machine. This is X plus Y, and then you have a node that represents that. And each node in this program represents where data flows out of that program. And so you could say, okay, basically the inputs to this, so this node is a addition, the plus, so it has two inputs, X and Y. X and Y get put in there. The computation happens, the addition, and then the result goes out on this graph to each of these two instructions. So on the left side, the 2 plus 3 will happen. I hope, gosh, that's 5 before I say it. And then it will compute 4. So it's a hard-coded 4 in here, minus 5, output to C, and it will keep flowing down the program. And then on the right branch, it will take 2 plus 3, which should be 5. 5 times 5 should output that as 25. And so, yeah, you can see actually they've done the step here. So if you look on the left side of figure 3, here you have the first step. And then as soon as this instruction is ready, and the very cool thing, since the data flow is encoded in the program, as soon as an instruction has its inputs and is ready, then it fires and executes. So as soon as this plus instruction has both of the inputs that's coming to it, it says, okay, 2 + 3 is 5, great, and send 5 along all of my outgoing edges. So this is 5 sent along all the outgoing edges here. And then if you add features like a branch instruction, so this is one value coming into this node, this weird branch in figure 4, one value coming into this node, and then a control bit. And if the control bit's true, then that value flows down the true branch. And if the value's false, it flows down the false branch. With that and a merge node, so a merge node is whatever the first node that goes into there is the one that goes out. With that, you can implement completely a computation. So just like you can do in a normal machine. So here's a pretty interesting, so this is their actual data flow machine. So they have in here a function to do, what is this, integrals or something, written in a Pascal-like language. So you can see it looks like a pretty normal, simple language. And then that gets translated down to this TASS assembly language. And this here is what then gets compiled into the data flow machine. So then here, this is the figure of essentially this data flow machine this data flow program that represents this machine. So this brief foray into computing history, and the cool idea here is essentially, let me go further. So if we look at, and this is the cool thing is this is a paper that was written in 1985. And so you can see their figures are beautiful and very detailed and takes you step by step through how this machine works. So in this figure 4, the black node, the colored nodes here are going to be the ones that execute. So this shows you how loops work in this machine. So you really have to spend time stepping through to understand how this works. And essentially how these machines work, and the whole point of why they tried to create these is say, how do you do parallel processing? So the entire idea behind a data flow machine is any instruction in the entire program or the entire machine can execute when it's ready. So rather than thinking about control flow and dealing with that, as soon as the data is ready for instruction, boom, it executes. So the idea being you could have as many processors running as you want to do that. And so let me skip forward. The really cool thing is it's not a theoretical exercise. This is an actual machine that they built. Here's the picture of this Manchester prototype data flow machine. And so let's see. Yeah, so you can do loops, you can do function calls, you can do all kinds of stuff. There's tricks you have to do to enable loops and function calls. But once you do that, you have everything you need. And so, and it may seem like, I don't know, this is just Adam being weird and digging into crazy computer architectures and implementing it to torture CTF players. And while that's partly true, the other thing this is not stuff that, even though, so your CPU that you're using right now, right, executes x86, ARM, MIPS, whatever, kind of the traditional notion of a processor that we think about, which is in that model of instructions that execute with an instruction pointer, fetch, execute, decode cycle, all that fun stuff. But under the hood, modern processors do out of order execution based on data flow. And so when your CPU translates your assembly language instructions to microcode, it can execute it out of order because it builds this graph and executes things as soon as they're ready. And all of that work and that research that went into this low-level optimization of CPUs is from this research in how do we make really insanely parallel machines. So that's kind of the background information on the challenge. The team's got none of this. They just got a binary called Manchester and a machine. And so I'm not going to go into all the details, but right now we have this great archive, like Jan said. So on the archive right now, we've just released, you can go and spin up Parallel AF and see if you can hack as well as the best hackers on the planet. So this lasted, do you have the times, Jan? I don't have it off the top of my head. So It wasn't exploited. We had the first version where that basically they couldn't write files. So that first version wasn't exploited in the first day.
So it took about 8 hours.
It took 8 plus,
16
right?
hours.
Yeah, 17 roughly hours. Yeah, so we launched with this challenge. So it took 17 hours for the teams to be able to reverse engineer it enough to trigger a backdoor that I'd put into a user space program. And then, oh yeah, I didn't mention this, but the system has an operating system and then user space program, a shell and user space programs, and has a loading system. So I had to write a high-level language with a compiler, an assembler, essentially a linker, all this fun stuff. But yeah, now you can download this, play this, see how you do on Parallel AF, and I'll be releasing the source code at the end of the CTF. Did I miss anything? I think that's it.
No, I think we're fairly good to go. So that's Parallel AF. The other challenge that has now been retired from DEF CON CTF is called Rorschach. Let me show it to you on also archive.oo. All right. Hopefully everyone can see that. So this is Rorschach. This is a challenge we created to explore the concept of adversarial machine learning and the usage and prevention of black box and white box adversarial ML attacks. So let me deconstruct what I just said. Let's unpack that. Machine learning is taking over the world at the moment. Everything runs on AI. You have things in your car that in my car, I guess there's a front-facing camera that tells me what the speed limit is, which is crazy. But it turns out that there's also a lot of problems with ML, a lot of security issues. It turns out that these machine learning models can be easily fooled by carefully modified images or carefully modified even physical objects that make the model think that an object is actually a different object. There's been a ton of interesting attacks developed. Researchers from Carnegie Mellon 3D printed masks that, sunglasses that when they wear sunglasses, of course, you can still like recognize that, this is Adam, this is Jan, et cetera, but with these
voice recognition.
Hmm?
What about voice recognition? They're also used for recognizing.
Oh yeah, absolutely. So, anyways, on voice as well. This sunglasses, they could 3D print sunglasses. You put them on, and a face recognition system thinks you're some celebrity or something, right? Same with voice recognition. There's been research into creating sounds that you cannot hear, but that Siri or Alexa think is your voice and responds to.
Dolphin attacks, right?
Yeah, it's called a dolphin attack because it's they use high pitched noises. Anyway, so there's this huge class.
And I thought it says you go.
Exactly. That sounds more like a fox.
What does the fox say?
Exactly. All right. So, anyways, machine learning is a big area, and when we started hosting DEF CON CTF, one of our hopes was to introduce this into Capture the Flag, following a trend in the last maybe 5 to 8 years of Capture the Flag that started introducing serious.
You froze or you stopped talking.
Am I back?
Yep.
Discord just asked me, how did the call go? Please click one of these. What the fuck? Anyways.
I think I'm still on this, so I think bad if you're asking.
Exactly. I clicked the frowny face. Anyways, in the last 5 to 8 years of DEF CON, of Capture the Flag in general, worldwide, there's been this trend toward exploring interesting crypto problems from the perspective of actual mathematical weaknesses of cryptography and so forth. usually in these problems, you have to either look at a secure cryptographic algorithm in an insecure setting, or you look at an insecure cryptographic algorithm custom tailored to have specific vulnerabilities that you have to find and break. This requires mathematical knowledge. I once built an entire whiteboard in the lab working on a challenge that took me 47 hours of the CTF to solve, which was really crazy. But we wanted to do something similar for machine learning. We wanted to explore this area, emerging area of security through capture the flag challenges. We started out with, in our first year, a challenge called Atom Tune, where teams had to synthesize voice prints matching Atom D.
Can I tell the story real quick?
Absolutely.
The monstrosity so he didn't really tell me the details of this. He just said vaguely, I'm going to do this thing with your voice, whatever. I was like, sure. So the night before DEF CON Quals, we got in a big house for all of us to stay in and host Quals in. And Jan and I think we're the only ones there that night. And so I wake up at probably like 7 or 8 and I like hear this noise in the living room. And I'm like, what the heck is that noise? And so I get up and it's like a horror movie. So I'm walking closer and closer to the kitchen. I'm like, oh my God, Jan stayed up all night till 7 a.m. He's still freaking like listening to my voice. How crazy. I go into the kitchen. I'm like, what's going on, Jan? And I look and it's his laptop. And I realize he's playing a sound of me saying, on loop for hours and hours and hours. He compiled a playlist of my, what do they call those? Inaudibles or whatever?
Yeah.
And just played it on the loop on his speakers in this Airbnb house that we were in for hours. And it woke me up. So it was terrifying. So don't trust his artist with anything is, I think, the key to that story.
Yep, there you go. So that, one second, let me get my mind back. This shift system is brutal because we aren't sleeping at all. So we created that Atom Tune challenge. That was super fun. Teams had a blast taking different approaches to synthesizing Atom's voice. We created different challenges based on recovering the training set used for a neural network. And this year, we created a different sort of challenge based on attacking the classification boundary of neural networks. So let me bring up some background real quick, and I'll go in depth. Oh, did I already share?
You are sharing your screen, in case you didn't know.
I'm sharing my screen. Yeah. Okay, so this is the challenge I'm talking about, rorschach. This is the background. This is a decision boundary of a neural network, and a very shitty, well, I mean, this is a great image for what it's trying to show, but it's a shitty attempt of mine at Googling for 5 minutes to find it. What happens here is when a neural network tries to learn to recognize different things, it makes essentially a mind map. And this mind map has areas that through various selection of parts of the image or voice or whatever of patterns that it identifies, it clusters essentially the attributes of whatever it's trying to recognize into different areas separated by a boundary. And anything on one side of the boundary is a cat, on the other side of the boundary, it's a dog. So this decision boundary is attackable, it turns out, by carefully crafting inputs. Even if you don't have access to the original neural network, you can carry out these boundary attacks, which place inputs right on the other side of a boundary to misclassify them as something, whatever thing that you want the neural network to classify them as. The kind of latest academic work in this area is called the hop, skip, jump attack. It is this attack on, or this paper that you can find on arXiv if you're interested in reading it. And the challenge, the idea was that teams would implement basically this hop, skip, jump attack by remotely querying the neural network, which was running on a different neural network, was running on every player's machine, to make it misclassify, to create images specifically designed to be classified as a certain thing. And every round you have to get a different classification. And if you got that classification, we managed to create an image to fool the network into classifying it as something, then the network, then the challenge would give you the flag. This whole area of what's called black box machine learning attacks, which is what happens when you don't have the model, is an active area of research. If you're interested, I highly recommend this talk at Usenix Enigma 2017, called Adversarial Examples in Machine Learning. The speaker goes through a lot of interesting parts of the field and culminates in a very early attack. 2017 was ancient history in AI, but an early attack that explains how you can basically fool neural networks that you don't have access to. The basic idea of this early attack is fairly clever. You don't have access to the remote network, but you have access to its classification result. It'll tell you this is a cat, this is a dog. So you do a bunch of queries of a bunch of random data, and then you train a replacement network locally by telling it this random thing was classified as a cat, this random thing was classified as a dog. Turns out there's some convergence there, not only of the classification result, but also of the kind of misclassification potential. If you can fool your local network that you've created, you can likely fool the resulting, or there's a high probability that you'll fool the original. This is the hop, skip, jump attack is a new version of this, and my hope was that teams would use this hop, skip, jump attack to get to right to the edge of the boundary, and then for defense, that teams would try to identify these boundary attacks and basically filter out any adversarial inputs that were too close to the boundary. I wanted to run this service half as a black box service, and then halfway through its lifetime, switch it to a white box service. So that's what we did. We ran Rorschach from day one. We ran it from shift one. We ran it for the basically 7 of the 8 hours, starting 1 hour in to let kind of the competition stabilize and so forth. And then we moved onwards into the white box phase. Right before the end of the first day, I released an update to the challenge that leaked everyone's models to each other. So then they could start attacking it in a white box way. And then this resulted in somewhat of quite a lot of chaos on the second day. And within more or less 3 hours on the second day, a team had captured so many flags that we shut down the service. So this is by design. In our competition, when one team has stolen 600 flags from one service, we consider that service to be done. That's how both Parallel and Rorschach were shut down. If you're interested, some search queries to look at while we're working through this challenge on Archive.oo. One query is boundary attack. So this is my image query to try to find that image. Like I mentioned, hop, skip, jump is the latest in this. It's a very math-heavy paper. It was very hard to make it through it, but if you're interested in kind of cutting edge, this is it. And then
compare it with a crypto paper.
It's
You're the mathy guy, so
yeah, it's different math. So I am more
summations as opposed to fields or something.
Yeah, it's like statistics as opposed to group theory. It's a crazy, very very interesting difference. Anyways, the hop, skip, jump attack is a super interesting paper. I highly recommend you read it just to get an idea of the challenges facing machine learning nowadays. If you have any questions, as usual, about parallel AF, reach out to Adam. About Rorschach, reach out to me. We might not be fully responsive during the CTF. There's a lot of other things to worry about, but afterwards we will get back to you with answers. Both of these challenges are now on archive.oo. We'll tweet out direct links. Give them a try. They're much easier on archive.oo because you can, spin it up, pull it down locally. These are actions that teams didn't necessarily have access to during the actual competition, but you can, of course, through self-discipline, limit yourself. For Rorschach, you can download the model, but see if you can also solve it without downloading it. Let's see. Oops, sorry about that. Other challenges in the game. Let me switch back to the other screen I was sharing. Other challenges. So I showed this view. We have several other challenges that we have played. One is Casino Life. So Casino Life is we talked about it yesterday, it's a blackjack simulator written in Conway's Game of Life. This challenge, we're going to talk about it in depth today, but it turns out there's still some life in this challenge left. So we'll save that to the third recap. This challenge is still live. Pinball is another challenge that is still live. This was the state as of the end. Sorry, I should explain this graph. This is the latest status vertically on the left side, right next to the names, and then it goes backwards in time as you go right. When it's green, it means the teams have improved their solution. This is a King of the Hill challenge in which teams are competing for the optimal solution. It is basically a gamified version of the code coverage problem, which is a very common problem in program analysis when you're trying to find vulnerabilities. That's
sorry, just to clarify, I mean, it means how can you give input that triggers as much of the binary as possible, or so yeah, how can you exercise as much functionality of an application as possible by giving it clever input?
Yeah, and this is basically the CTF challenge designed around that concept. It is still live and will likely be live for a while today. As
depends on the teams. These are the best teams in the world.
Exactly. They might kill it pretty quick, but we'll see. This is Rorschach. I think I already showed it. So here is the final state, how many flags were captured by each team. The top team for Rorschach, the team that's shut it down, is Samurai. This is their row here.
A lot of flags.
It's a lot of flags. They got over 600 flags, shut the service down. Turns out they seem to be some pretty heavy-duty machine learning experts. But everyone, almost everyone, scored some amounts on this challenge. It was quite an active challenge for a while. This is, on the other hand, the parallel challenge that Adam described. So you can see this one is a much more intricate, tricky challenge. Only 1, 2, 3, 4, 5 of the 16 teams managed to get any flags at all.
And that was on the first version that we released that had a basic backdoor that they couldn't write or load code. So when the first team got 200 out of the 600 flags, we switched over to the second version that removed that backdoor, but allowed them the functionality to write. So they could write to files and load files in the parallel machine. And there were a number of vulnerabilities in there.
Here you can see kind of the number of ticks from the last flag. I don't remember if we mentioned this. Oh yeah, the ticks are 5 minutes. That's when we update flags.
6 minutes. 6 minutes, man.
6 minutes, sorry. Here you can see that PPP had ticks up to when the service was, or flags up to when the service was retired 24 ticks ago. For 40 ticks before that, none of the other teams scored, because 40 ticks before that, we made this update so that they had to figure out more parts of the challenge This is an idea that we've been exploring to kind of keep challenges alive by continually updating, just like real software continues to.
And one of the really interesting things, Jan, if we can look at this quickly, if you look at the Team 4 stolen column, so how many flags were stolen from HitCon Balsan? Right, only one team was able to.
No, Team 7.
No, 3. No, I meant Team 4 because they never exploited it, but they must have patched it, right? So they didn't actually have an exploit, but so this service was open patching because people could cat out each other's, like in the game, cat out other people's OS and machines and stuff. So you could maybe, I don't actually know this, I didn't look in, but one way to interpret this is they probably deployed somebody else's patch and it fixed the vulnerability, and they didn't yet figure out how to exploit that, but by using somebody else's patch, they were able to get around it.
That's one possibility. Yeah. Team 7 is interesting. They had full exploitation and they had a patch. No one was exploiting them. And no one ever exploited them through the whole lifetime of this challenge.
No, through phase 1. PvP exploited them. Look.
Yeah, PvP exploited them in phase 2.
Phase 2.
Pretty interesting. All right. This is one of the challenges that we launched yesterday. Role hacking game. Sorry.
Role hacker game. Like role playing. Role hacking. Okay, yeah, role hacking game.
You can see it is quite active. So role hacking game is a game. Let me bring up a visualization of it. 1 second. Actually, never mind. It doesn't seem to be up right now. So you can see a visualization of it on the public scoreboard when the game resumes, basically showing the state of the game. It's a online, simple little game where there are very intricate vulnerabilities that are very complicated that allows teams to steal each other's flags. And in this case, the flag is an actual item in the game. So this is a very kind of different sort of challenge that has this centralized component where teams are directly interfacing with each other. So this is the summary of the services so far. I mentioned directly interfacing with each other.
Jan, let me share my screen, and I have a image I've captured of Yannick's challenge.
Perfect.
Or of RHG. All right. Cool. So yeah, as Jan said, so there's a lot of depth to this challenge, but eventually, so at the public scoreboard, you can see basically this grid layout that has a number of things in it. So you can see there's a number of players. There's a number of, so the players 1 through 16 for each of the 16 teams. You can see actually the names of the players. And they're playing this game essentially in this grid. And if you hover over each of these items, you can see that like each of the things in this grid is a different thing. There's items that they can pick up and buy. There's attacks they can launch. So there's things that they can do in the game. Each player has money. They can pick up items. They can kill players, which causes them to drop their flag. And other players can pick up their flag and submit it and break it. So it's a very, very cool challenge that you can kind of watch the teams evolve. So when we launch in an hour and 20 minutes or an hour and 10 minutes, then you should definitely check that out. Cool.
All right. So one thing I want to mention is we tried to build a theme of direct interaction between hackers because we can't do that in person right now. So we tried to build it in to many of these challenges. Role hacking game is literally a game that they play directly with each other. Similarly, Rorschach, my idea was that they would be playing a cat and mouse game with their patches and the attacks that bypass them. And in Casino Life, they're playing blackjack against each other. We have other challenges on the way. We have another recap partway through the final phase of the game tomorrow, and we will tweet about that.
What is that? 23 hours, 22 hours, something like that. So
yeah.
Sunday at noon, we will do another public recap, and I'm sure we'll be even more well-rested and fully functional. So, you know, tune in to see us at our very, very best on the last day of DEF CON CTF.
Exactly. All right. Thank you very much.
We got a game to set up. See ya. Bye.
Yep.